Hello guys, today we're gonna start with lecture 11. Let's see. We're gonna go basically over Boolean algebra. We're not gonna give anything new. It's an example that will do most of the stuff we took in the Boolean algebra. Usually this is useful for your computer organization also. We're gonna cover most of this in the computer organization. And usually I give one question in the final. It's an A question. If you get that question, you get an A in the whole class. Last semester, nobody answered it. The semester before that, I had maybe 2 almost gonna answer it, but they didn't. And this question is similar a little bit to what I gave them. So let's take it at I'll give you this Boolean expression. We said, how can we describe Boolean algebra? 3 ways. Either an expression, an equation, a logical diagram, and a truth table. Those 3 to describe Boolean algebra. Now what am I asking you? Find the truth table, find the sum of product, and here we need to find the product of sum, POS, SOP and POS. Draw the logical diagram, simplify both ways, which is using the Boolean rules, and what? And the K-maps. We took lecture 10. Draw the circuit or implement the circuit using just NAND, NOR gates. Draw the circuit using just OR gates. This is what we're gonna take in this lecture. So this is our equation. Let's see, how do we start? If you need to draw the truth table, what do we need? How do we start? Check how many variables I have. I have 1, 2, A, C, D. The complements considered D, so don't worry about it. So I have 3. I don't have B. Be careful. I don't have a B. I only have 3 variables. So how many rows am I gonna have? I'm gonna have 8 rows. And remember, we start from 0 to 7 usually. And here's A, C, D. And now what do I start? I mark them as 0, 1, 2, 3, 4. And what are those gonna be? Those are gonna be the Boolean, the binary value for 0. So here we put 1. 0 was the binary value of 0 using 3 variables. That's 0 was the binary value for 1. What's the binary value for 2? For 3. This is the easiest way. Oh, sorry. And this represents what? All possible values for A, C, and D. This is the easiest way to do it. I found out this is the easiest way. If I had 4 variables, I'll have 2 to the power of 4. Goes from what? 0 to 15. So let's start. This is 0. 1, 2, 3. Oh, this will give me 5. This is 3. Okay, I fixed it. And then, okay, this is good. 4, 5, 6. It was 6. So this one was 6, 4, and 2. This is 1, 2, and 4 from 1 to the power 0, to the power 1, to the power 2, converting to decimal to binary. 1, 2, 4. That's why this is 6. This is 4 and 2, 6. This is 2 and 1, 3. This is 4 by itself. This is 5. And last one I have 7. Now how would I start? Usually I take the first expression and it's A plus C. So I put A or C and I find the result. 0 or 0 is 0. 0 or 0 is 0. 0 or 1 is 1. 0 or 1 is 1, and we find all of those. 1 or 1 is 1, 1, and we find all of those. Now what do we need to do? I'll do this. I'll take AD, find it by itself. AD. A and D. Now change, it's not an OR. A and D. 0 and 0 is 0. 0 and 1 is 0. 0 and 0 is 0. 0 and 1 is 0. All those are going to give me 0 except this one and this one. 1 and 1 is going to give me 1. Now I'll go to this one and I'll find D prime by itself. Makes it easier. So this is going to be 1. Just flip every 0 to 1 and for what? The D. Go. Then I'll find A and D now, which is this and this. So what is it going to be? And we have an AND. There's going to be 0. Anyone that has 0, 0, 0, and 0, 1, 0, 1, 0. Now I'll do both of those, which is this and this. So what can I get? AD or AD not? 0, 0, 0, 0. This is an OR. 1, 1, 1, 1. Now I'll find AC, which is this and this, and they're ANDed. So I'll have 0, 0, 0, 0, ooh, and here's the rest of them. 1, 1, 1. Now I'll find A and C, or with this I could have done it with all of them, yeah, but that's not going to make a difference. AC or C is going to be what? 0, this and this, 0, 0, 0, 0, 1, 1, 0, 0, 1. Now what do we do? I'll take either those and those, or those and those, whatever. But let's start with those. A or C, AD, or which is, we have this and we have AC. So they're going to be those two. I call the function 1, so we don't have space for all this. So this and this, what are they going to be? And it 0, 0, 0, 0, 1, 1, 1. Now what we do? I'll do this one, F1 with this, or this and this, or 0, 0, 1, 1, all of them ones. This is an OR. So now we have the truth table. What did they ask for? Then they asked for sum of product, S, OP. So I go and take the ones. This is a 1. This is a 1. Mainly I'll take all of those ones as sum of product. How's that? What's this one? What does this one represent? This one represents what? I look here. A na, C, and D na. A na, C, D na. So I'll have it as A na. Let's go here. C and D na. This is sum of products plus what? Plus 0 is what? A na. No, I'm taking the second one. Taking this one. And I have A na, C, and D. 0 is not, and 1 is what? Without a not. The original number. D. Then what do I have? I have this third one, which is A C naught D naught plus A C naught D naught. And this is what? Sum of products. Find the truth table, find the sum of products. Here's the truth table. I just took the last one, so this will make it easier. So we're going to take those. So what's this? We're going to take those. This is A naught C D naught. And here's A naught C D, A C naught D naught, A C naught D, A C D naught, A C D. And all of those are sum of products. This is my sum of products. How do I get my product of sum? It's going to be this and what? Zeros. And they're going to be ORs with ANDs. This is AND. And what's my OR? It's A naught C naught or C naught or D naught. Same here. What do I have? A naught or C naught plus or D. This is my product of sum. Oh, this one. Sorry, I fixed this before earlier and I forgot to take this out. No, take this out. It's going to be this. Because I figured out that was a 0. Now draw the logic diagram. How do we draw the logic diagram? Remember, we had one. We can go online and draw it. Let's see, what do we want? We need our Boolean Algebra simulator. Let's see what we can get here. I think this was a good one. We'll go with this. Though I didn't like it, but let's see what's my equation. It was A or C, I think. A or C, so I need an OR gate. This representing down. See why I had this one sometimes starts. Let's go try another one. Now simulator. This one. Sorry guys about that. Let's see. It was a good one that I simulated and simulated surface. Mm, this one. Okay, let's try this one. We needed an OR gate. This is what it was. XOR OR gate. This comes with two labels. I can put this one. This is not. Okay. Let's see here. Let's consider them as what? A and C. I have an OR gate. Then I had for those landed with A and D. A and D. And also A and D now. So let's put this as A. Those two as A. And I needed a D. And what we can do is put a D naught, an inverter, or I put a wholly new one, or I'll take this and put an inverter for it. NOT gate. This is a buffer. This is a NOT gate. And this is D naught. I could have labeled them, but I don't want to do that. So it doesn't become. This is A or C. This is A D naught. And what was the relation between them? We had an OR between them. There's an OR. There's an OR. And between this and this, we had an AND, which is basically, I'm saying, this OR was what? This, and now the AND I'm writing in between those. Okay, so AND is between those, let's do it this way, so we have space. Then I have the A, those are ANDed together, and they are ORed with the AC. So okay, let's get the AC. No, this is not an OR, this is an OR. Let's put A and C, consider those as A and C. A or C, sorry. Those two are OR together, which is basically this one, and now I OR them. I have this and OR to AND it. Oh, sorry, I did a mistake. Okay. Fix our mistake. I'm going to take this out. again. Okay, and gate. This is the A and C. And now I need an OR between them, which is this OR. I have the AC and it, and I have all the rest also and it together, and now I'll OR both of those, and I OR it at the end with a C. So here's another OR, those two OR together. And now I have, this will give me what? All this I'm gonna OR it will give me this. Now I'm gonna OR it with a C. Now if you wanna OR it with a C, let's consider this as the AC, remember from the previous one? Or I can put a new C, but this will be better. Let's do this. And this will be my output for that circuit. So this drawing that circuit and logic diagram. Okay, now drawing, now I'm doing the simplification, I think. And here's what I did. I started with the last one, AC plus C equals what? C. We had the rule. Remember Boolean Algebra rules. This is one of the important rules. AC plus C equals C. Now what can I do here? Can I take the A common between the D's? I can't take D's because I have D complement, but I can take the A. I can take this as a common, and I'll have D or D naught. I plus this plus C plus D or D naught. If I add 0 or 1, 1 or 0, what is it going to give me? 1. So all this equals what? 1. D or D naught equals 1. I have A 1. A and 1 is going to always be what? A, not 1. Because 0 and 1 is 0. 1 and 1 is 1. Okay. Now what can I do here? Let's see, we need to distribute this and this. So I'll have AA and AC plus well C, which is this one, or C. So this is A, this is AC or C. So I can either take those as C or take those as A, either one. So I took this as C, I'm left with what? A or C. A or C. This simplification using Boolean rules. Now K-maps, we need the truth table, yeah? We need the truth table, so I'm gonna need all those. So did I copy those? Okay, so I need, here we're gonna put what? A naught, C naught, which is 0, 0, think of it. 0, 1, what's 0, 1? A naught and C, and now here what do I put? 1, 1, which is A and C. And why did we do that? We need to change only one variable each time. Here I had A naught, C naught, and I changed the C to from C naught to C, and now I changed the A. I can't change both. I can say C naught and A. I can do this. I can do this, but I already have it. So what we do here is A, C, which is 1, 1. And here what we'll have is the last one, A, C naught. And let's try to do it. And what do we have here? We can have B naught and D, which is 0 and 1. And here what's A naught, C, and D naught. Let's make it here. A naught, I have this and this A naught with C, with C naught, this is C, so those two, with D naught, so this is 1. Then I have A naught, this and this, with C, this, with D, this. This is a 1. Now I have A, C naught, with D, so it's this, so this. Now I have A, C naught with D naught. I have AC with D naught and ACD, which is this. I read those, this and this. So this is the first one. Now the grouping, to simplify, I need to group. I can either take what? Those two and those two, those four and those two, or I can do this and this, which will be better, more simplified. You have to group as much as you can, or what? Some people might take this and this, but I need to group as much as I can, so I have those four of them be the same. So what does those four represent? Those four represent A, what's common between A, C and C naught, they're not common. D, D naught are not common. What's common between those four? It's going to be the C. So I'll have A plus C. This is the C and this is the A. And what did I get when I simplified using rules? We got A or C, and this gave us the same thing. A or C, so that's right. This gave us C, this gave us A. Draw the circuit using just NAND gates. Here I have what? An OR gate. A or C is an OR gate. How can I do it using a NAND gate? And here's what we do. Remember, De Morgan is really important. I'll have a double complement on it. So now, what do we do? Distribute the first complement. It's going to be A naught and C naught. What's this gate? This is an AND with a NOT, with this NOT. It's a NAND. So I'm going to have a NAND, A naught, C naught. We can put here inverters, the NOT gate, and I have A, C. And this one, okay, this one is for example. It's not the same one, but I gave you an example to explain that one. Let's say for an XOR. An XOR is, this is the truth table for an XOR. And if I draw, always get the truth table for any, and draw the sum of products. And what you do is double complement for the sum of products. So what's the sum of product for an XOR? It's this, which is A not B and A B not. Or A. If we double complement this, what will we have now? I'm going to have A not B complemented, both of those, and this is translated to what? An AND gate with A B not complemented, and this is an AND. This is an AND, yeah? So now I have here A now. So if I distribute this complement, what I have here, I'll have A now, not double now. Let's put them this way. Or can I do it this way? Should you continue or no? What do you think? No, because this is going to change it to an OR. What's this? This is an AND. This is an AND. This is an AND. So here I have 3 NAND gates. You stop here. You stop on this one. So what about, they asked if we need NORs, that way to implement it in NORs, yeah? Let's see, this is the complement. If I distribute this, this is the NAND. And this is an AND gate, and this is an AND gate. But they had a question, do it in NOR gates also, yeah? Now did it add it in this slide? Where did the question go? I passed it. Draw the circuit using just OR gates. How would you draw it in NOR gates? NOR or OR gates? Sorry, it should be NOR gates. It's already NOR gates, so how would I draw it in NOR gates? I'll take the products of sum for them. Here I took the sum of products. I'll take the products of sum, which is what? Different than the sum of products. Sum of products will convert to NANDs, and products of sum will convert to NORs when I add the two's complements. So take the product of sum and put a double complement on it. And I showed you at the beginning of the class how we take the product of sum. We take the zeros, we look at the zeros, not on the ones, and we all NAND them together. NAND the ORs. Guys, this is a really important one. You need to know it. Focus on it, you'll get it. But the problem is you have to know everything about Boolean algebra. If you have a mistake in any one of those, it might screw your whole answers. So please try another example. For example, I can tell you, draw me them the AND gate using NAND gates only. Using NAND gates, and I didn't explain this the last time. NAND and NOR are considered universal gates. And what do I mean by universal gate? They are used, if you use NAND gates, it's much better for any circuit. They're used more widely. Why? They use less transistors. NAND and NOR gates use less transistors. So if I can convert my whole circuit to NANDs and NORs, that's much better. That's what? Less in price, less in heat, and more speed. NAND and NOR are universal gates, meaning they are used wider, they're preferred more than the others. They use less transistors. Please guys, if you have any questions, leave it in the description below. Thank you, and see you next lecture.